Okay, moving on to part D, we're asked to find the bending stress and torsional shear stress at the point of maximum bending moment. So let's take a look again at our shear force and bending moment diagrams that we developed in the last part of this problem. And we see that the point of maximum bending moment is right here. And that is going to be right at the middle of pulley B. So we need to find the bending stress and torsional shear stress at this point. All right, so let's start with the bending stress. We can use our flexure formula, which tells us that the bending stress is going to be equal to the bending moment times y, which is the distance from our neutral axis to the point that we're interested in, and divided by I, which is our area moment of inertia. So before we dive into that, let's take a look at what's happening here at our section right around this point B, or pulley B. We have a bending moment that is causing a stress to develop in this beam, and our bending moment is negative, which means that we're bending downwards here. So I think of negative bending moment as a frowny face, positive bending moment is a smiley face. We're bending downwards, and that means that the fibers on the top of this beam are getting stretched, right? You can imagine that we're pulling apart the fibers here, and the fibers at the bottom here are getting compressed. So for most materials, we're going to worry more about tension than we are about compression. So let's consider the stress at this top point of the beam. And that is going to be at a distance from the neutral axis for a solid circular shaft that's equal to the radius of the shaft. So this is our distance y that we need, and it's equal to our radius. We were given that this is a 30 millimeter diameter shaft, so that's 15 millimeters for our radius. And the other thing we need here is that the area moment of inertia for a solid circular rod is going to be equal to pi times r to the 4th power over 4. And you can find this in lookup tables in the back of the Shigley textbook. You can also find it anywhere online. It's in the PE handbook. So now let's plug in our numbers here. We've got pi times 0.015 meters to the 4th power over 4. So this is going to give us a really small number. And then let's plug that into our flexure formula. So our stress is going to be equal to 698 Newton meters times our radius, 0.015 meters, divided by this very small number, I, and so that's going to give us a very big number for our stress. So keep that in mind. The smaller the radius of your beam, that goes to the power of 4. So as you decrease the radius of your shaft, you are going to increase the bending stress by a very significant magnitude. So let me plug all of this into my calculator. Got 698 Newton meters times 0.015 divided by pi divided by 0.015 to the 4th power times 4. Okay, so I get about 263 megapascals. So I'm dividing my answer by 10 to the 6 to get the megapascal, and that leaves me with 263. Okay, so we've got our bending moment. Now we also need our torsional shear stress, and our formula for that is tau equal to T for torsion times our radius divided by J. Now J is similar to I. It's the polar moment of inertia, and again you can look that up in a table. For a solid circular shaft, it's going to be pi r to the 4th over 2, so just half of I, twice I, and then we're going to plug in our value for torque, and let's look at what kind of torque we have acting at this point. So we have our belt tensions T1 and T2 that are causing a torque to develop on point B. So this is going to be our T1 times, sorry, I have to go back and forth so many times. This distance, which is 125 millimeters. Let me just copy this. I'm going to need these numbers. Okay, so our distance of 125 millimeters for T1, and then T2 is acting in the opposite direction, so we'll give that a minus. T2 also times 125 millimeters. And R is the radius of the shaft. That's the distance that this torsion, that's the distance that we want our shear stress from the center of our cross section. So remember that when we're talking about torsional stresses that develop in a beam, they're going to be 0 at the center and maximum at the outside. Imagine twisting a flexible bar. You're not going to be doing anything to the fibers in the center, and then as you get further and further out from the center, you're going to be stretching those fibers more and more. So this distance R is the distance from the center to this most stretched fiber on the outside, which is our distance R. So that's 0.015 meters, and divided by our polar area moment of inertia, so 0.015 meters to the 4th power over 2. Let's plug in all of our numbers here. So 2,880 times 0.125 minus 432 times 0.125. Multiply that by 0.015 and divide by our polar area moment of inertia. All right, I got a value of 57.7 megapascals. So I divided my final answer by 10 to the 6, and that gave me my answer in megapascals. Okay, so here's our our bending stress and our shear stress at the point of maximum moment in our beam.